Hello, everyone. Thank you for joining us for today's session with CPFD, our Advanced Partner Alliance member. Today, we are going to be presenting our latest addition to the APA, that is Arena Flow by CPFD. A few housekeeping notes before we begin. The presentation will last about 45 minutes, and afterwards, we will have a Q&A session. So if you don't have any questions, please feel free to use the chat box, and questions will be addressed at the end of the session. Today's presenters are Peter Blazer, Vice President of Operations, and Thomas Brandt, Manager of Foundry Products and Services from CPFD team. Welcome, Peter and Thomas. We are happy that you can present to us today and start your presentation when you're ready. Thank you.
All right. Well, thank you, Octavio, and hello, everybody. Good morning, and for those of you in Europe and Asia, good afternoon, good evening. Hope you're having a good night. It is my pleasure to present Arena Flow, the latest addition to the APA. Arena Flow is specialty foundry software for sand cores and molds. The outline of this particular webinar today is I am going to begin by giving a brief overview of our company and specifically the Arena Flow product, how it's used. We'll look at three short use cases, and then we're going to launch into a live demonstration of my colleague Thomas. And we've intentionally left considerable time for Q&A to be able to answer your questions. So please do not hesitate to put them in the Q&A panel as we go. So our company, CPFD Software, we are advancing multi-phase simulation and technology specifically for gas particle systems since 2003. We have two software products. Barracuda Virtual Reactor is already available on the APA, and that's our general purpose tool for broad applications for fluid particle systems, such as fluidized bed reactors. So that's for gas particle and liquid particle systems. It solves the coupled multi-phase hydrodynamics, so that's the gas particle or liquid particle motion, heat transfer, and chemical reactions in industrial scale units going to full commercial size. I won't say more about that, but that is available on the APA. And today, we're excited to introduce Arena Flow, which was new to the APA. It's available today. It is foundry-specific software for sand cores and molds. And it's used in different ways. Realistically, it's used for tooling that's right the first time to avoid the rework. It replaces that trial and error with virtual testing while at the same time augmenting your core making knowledge to understand not just what happens if I change sand or blow tubes or vents, but why, and to be able to capture and retain that core making knowledge. It's used to understand and then eliminate scrap, optimize cycle times, minimize dosage for amine or other consumables, and really increase the uptime while extending tool life. The end goal is to reduce costs, whether that's capital costs, and we'll look at that in one of the examples, operational cost, energy savings, and so forth. And there are a few different application areas for this. So first is in blowing or shooting the core. This is filling it, looking at how the sand is coming into the tooling. And I'm going to pause for a moment. Octavio, is my screen coming across? It looks in the one window as though it's still on the title slide. Can you verify that?
Yeah. We're now seeing the application now, areas and blowing machine.
Perfect. Well, this is a new tool. Thank you, and bear with me. So I'll do the slide again. So first of all, the application is blowing and shooting of cores. This is looking how the sand comes into the tooling. At the top, we're looking at the sand colored by compaction. In the middle, we're looking at the speed, how the speed is as it's filling the tooling. And at the bottom, we're looking at how that all comes together to impact final core density. Not just does the sand completely compact in the core, but how and what is the resulting core density and variations thereof. Next is for cold box cores, the curing, the progression of amine or SO2 through the through the tooling itself, looking at things like the first to cure areas, which are indications of you're probably using excessive consumables dosage, and last to cure, which is typically affecting your cycle times. For inorganic systems, we're looking at the temperature of the air, the sand, the moisture in the core being dried out, and then going into the gas phase and coming out. Is it redepositing elsewhere? Is it over drying? So for inorganic heating and dehydration. And then it's not just individual cores. It can be entire magazine simulations, looking at how the airflow and sand interact in the magazine. Do all the cavities fill the same way? If it's multiple cavities on a machine, perhaps it's a family box with different cores, or it could be large cores that may necessitate a double blow. We'll look at that in a moment. And it's used for a variety of processes. Historically, it's been used extensively for cold box, but it's increasingly being used for shell sand cores, for inorganics, for green sand systems, and other systems as well. So really, ArenaFlow is for air-driven sand motion. And so let's look at a few things that are unique to ArenaFlow. Why use it for cores and molds? Well, first of all, that's what it's built for. So this is not general purpose CFD software. It is specialty software, and we'll see that in the demonstration. The interface speaks the language of sand cores and molds, starting with your process, what your sand looks like, where your tubes and vents are located, and is an intuitive interface custom built for sand cores and molds. It also treats sand as discrete entities. Sand has a size distribution. Sand has unique densities, a silica sand shown here, or it could be a zircon or some sort of manufactured material, ceramic, all with different particle size distributions and densities. And ArenaFlow captures that. And uniquely, it captures the air-driven sand motion. Sand isn't metal. It doesn't just fall down under gravity. It's actually the air flow in the tooling that drags the sand into location. I love this animation that should be looping on the screen. When the tooling is empty, there's lots of airflow, and you see the sand colored by speed. So that red color indicates that sand is rapidly moving up. And then as those vents begin to plug, you have less airflow, and as a result, you have less sand speed, a lower sand speed, which is going to affect compaction. And while this is sort of a demonstration core, it demonstrates that, yeah, you can move sand uphill depending on the airflow. And ArenaFlow is able to capture that. ArenaFlow also has process-specific modules. So whether you're doing a blowing or shooting of a binder-coated sand or shell sand, cold box, inorganics, or the curing, is it a gas curing, such as the cold box process? Is it inorganic curing? And so ArenaFlow has an intuitive interface depending on what you are trying to simulate. It does have powerful and extensible post-processing. So the integrated post-processing enables you to do things like visualizations, rotations, plots. And I say it's extensible because you also have access to the raw data should you wish to script any of this. And it's award-winning technology. You know, going back to the early days in 2003 from the AFS, we were honored with the Howard F. Taylor Award for the most impactful paper for the metal casting industry. It's some work with General Motors. Back in 2010, the Applied Research Award was also awarded to us. And more recently, we were a winner here at CPFD of Best Software Technology. And really another thing that's maybe the last thing I'll point out here that's unique is that you do get support, first of all, from humans, and humans with a team of decades of experience in the metal casting, or in this case, the sand core arena. And so let's look at it briefly. So here is a video showing ArenaFlow used for the core. The pattern forming surfaces are in the middle. All these tubes, in this case, are an integrated core print. It's cold box process, so the sand begins the blow in the tubes. The air escapes through individual vents. And then we begin to look at how it's filling. How does that sand flow into the tooling? And not just looking at the sand color, but what is the density of that sand as it comes in? So we're seeing areas that are mostly filled. There's a large core print on the side that is being filled with high-speed sand, so that's still filling well. And then there's these areas in these critical pattern-forming surfaces in the middle that we're slowly filling. And so we're able to predict areas with potential defects. And then similarly, we're able to then predict what happens as you change blow tubes, as you change venting or parting line strategy. If you had different sands, begin to do that virtual testing to optimize the core in the virtual space. So just before we launch into that demo, let's look at 3 short case studies. The first is foundry. It's actually a Quebec foundry, faced production challenges for a water pump housing. This is for a portable fire pump. It was originally cast in green sand, and the process engineers wanted to convert to vertical pouring to reduce turbulence and improve quality. And so they wanted to convert the process. And so our partner, Lempe Reich, partnered with Foundry to optimize this. And ArenaFlow used as part of that tooling design, and they switched to the cold box process to identify the most effective means of shooting and gassing the cores and molds. And using ArenaFlow, the foundry was actually achieved increased quality with significantly reduced cooling cost and rapid time from concept to casting. I realize this is a really short overview. It was published in the July issue of Modern Casting. There is the link here. And I believe this will be available then afterwards for playback or contact us. We can send links to this. We'll also be going into more details on this case next week at the AFS Metal Casting Congress. And I'll be excited to have Lempe Reich share more of their story there. So the first case, process conversion, starting up new tooling with a different process, getting castings that are right, getting tooling cores that are right the first time. In this case, they actually then the first casting pour resulted in a viable casting. Another use case, this is a cycle time reduction. This was published over a decade ago in Modern Casting as well. This was a US OEM foundry that produced an engine head core that was taking significantly longer to cure than the cycle time allowed. So what they had to do to keep up with production is they put another core machine on the line, increasing the cost, obviously, to the additional tooling, the additional core machine, and the personnel to run it. And so ArenaFlow predicted what was happening. So if you look in the image on the right, you can see some of the last to cure regions in the core. Several alternatives were simulated with added vents. And you got to be careful here. It's easy to add vents to increase cycle time, and pretty quickly your tooling looks like Swiss cheese. You can be introducing your dosing, and you could have other issues. And so here it was optimizing the virtual space first. We also looked at the blowing to make sure there was no issues on filling that core, using the one that had the fastest cure time. And then it was verified in the software prior to implementing changes at this particular Midwest foundry. And then as a result, the solution that ArenaFlow suggested, or that was verified in ArenaFlow, allowed the core making operation to run as originally planned, so they could go back to having to remove that excess machine, the excess shift. And the foundry actually now simulates all new tooling with ArenaFlow to ensure it is right the first time. So process conversion, cycle time reduction. The last example is simply process variability control and scrap. This was a North American foundry. They made aluminum cylinder block castings, and they had an intermittent scrap issue. They had a low density in the webbing of the water jacket, and it was actually quite counterintuitive. When they simulated the issue, what they found is an unbalanced filling. So in this case, they had equal tubes on each side, but a lot more volume because this core prints on the right side is shown. And what happened is one side filled up faster, and when it did, there was a pressure change due to the blow tubes being filled, and all of a sudden you had this imbalance where sand that was flowing one way through the webbing turned and flowed a different way. And if that was not locked in, tightly compacted, it didn't move. And you'd start to see, I don't know if my mouse comes across, but right in that webbing, you'd start to see things opening up where you could see through it at times. And so they were able to, once they could understand what was happening, then they had a simple solution, again, implemented the tooling change. And really this illustrates that by using ArenaFlow up front in the tooling process, the entire situation could be avoided. Again, ArenaFlow is used to make tooling and cores and molds that are right the first time. And with that, we're going to launch into the demo. So we're going to show you ArenaFlow in action. So Thomas, get ready for that. One thing we're going to do here is we're just going to show an overview of the interface being straightforward to use, speaking your language, and also we're not going to go through every interface. We're going to look at some examples of core blowing and shooting, but there are other interfaces for curing as well. So I'm going to introduce Thomas Brunt. Thomas has over 35 years experience related to this: CAD, CAM, pattern making, tooling design, extensive work at a foundry product supplier, and simulation software as well. In fact, he's worked with the ArenaFlow software at various companies now for nearly 20 years, and we're honored to have him join us last year as our manager of foundry products and services. So with that, Thomas, I'm going to turn this over to you.
Thank you, Peter. My screen is coming through. So as Peter mentioned, this is our splash screen. That's the first part of the GUI you see. So we have various modules: binder coated sand for cold box, shell sand, any hot cured process, any binder coated sand that is cured with heat, inorganic curing, gas curing related to cold box. And one thing that is very useful is now we have our user manual. It's directly, you can directly access it and open it. No, it's not hidden by any support site or any access. It's installed as a local copy on your computer when you have ArenaFlow installed. So this morning, afternoon, evening, I will focus on binder coated sand or the cold box process. So let me click up and select a predefined setup. Now, if you follow those steps here on the left side, and you make sure that you come across all the tabs in order, you will go through any step that is needed to run the simulation, and finally post-processing with TechPlot. So grid generation, you load STL files. That's the only input. STL is the only input that ArenaFlow currently accepts. So create a grid. Typically, you would apply that using uniform cell count, which has benefits with regard to runtime. Now you can manually, using the controls here on this side, add or move lines around. Once you've done that, generate a grid, check the output, which I'm going to do here. So that loads up TechPlot, shows the default mesh lines. We can actually, click if you just want to see a shaded STL representation. What I like to do is having a predefined layout, which I'm going to load and just show the grid. So we got all 4 grid views synchronized, and we can actually zoom in and say, look at how is the resolution. Yeah, sure, we have a sharp corner here, which is obviously turned into a chamfer, but it's negligible. We got good resolution on our blow tube core interface, which is fairly important. And then, when we're satisfied with our grid, continue to the next step, which is defining in which direction particles and sand are influenced by gravity. Normally that would be negative set. Sand type. So here we define as Peter showed earlier, we define our particle distribution, percent retained, and particle size. So this is critical input and should match what you're using in production for the most accurate results. But again, this is just available process data. No modification is loaded in. Make sure you create a sent data. That's it. So that's defined. You can have multiple materials. You can have sand and additives. All you need is a screen and particle material density. Sand location. Tell the software where our sand resides initially. For cold box, that would be, commonly speaking, in the magazine and the tubes. Some level of sand in the tubes. That is defined. Define our blow pressure. So that can be either applied as a constant pressure, or in this case, created a pressure profile. Applied, and this is applied either at the top of the magazine, top of the sand plenum, or accurately described through where your pipe goes into, where your air inlets are connected to your blowhead, where you apply the pressure, where you pressurize the sand. Vents definition. So in this case, a set of predefined vents. So these vent locations are extracted from CAD and via an interface loaded into ArenaFlow as a predefined vent locations. So you have data that matches your tool design. You can either, if you have an in-house pattern shop, you can directly exchange that data, or you can exchange that data with an external pattern tool shop. But all those values are as you run them in production. Time control. This is a duration. This is the physical duration on your machine. And so if you anticipate, well, small core, we're going to see what happens up till 1 second. Most machines do not run shorter than 1 second. Above, they might go in a tenth of a second or half a second increments. But realistically, number of files output. So in this case, we can see results for every 100th of a second. Models, though, this is kind of the default settings, not visually, but how the solver actually runs. Local density, if we turn that off, we will not account for particle size and local density. We'll just get a general overview. Tool wear, so we have the ability to predict tool wear and corresponding wear settings, like if you got a softer material, you may want to change those, but these are the angle of impact and how they are influenced. We got resin wipe off, so we have a ability to predict how much resin is actually left on the surface as the sand grains hits and bounces around. So this would be your total binder fraction, part 1 and part 2 combined. Sand flowability. So this takes into account, not as a value, but it takes into account, your granular shape, your binder percentage, your surface area, and concentrates all that to a slider setting. So this would be the default uses for cold box for fairly round grain and probably a binder percentage in around 1.4, 1.5. Data output, so gives you option to add, subtract, this is your output data. This is what you can visualize. One thing, if you're multiple materials, you might consider turning particle species on for cells as well as it's already turned on for particles, etc. But default settings are pretty good. It's a really good starting point. Transient data can add local sensors, sensor points, similar to like a thermocouple in a casting mold. So we can record pressure, particle volume fraction, air speed in X, Y, and Z, particle speed X, Y, Z, and delta time. And the last four are specific to inorganic curing. So give that. And have those local recordings available. We have the option to use flux planes or screens that will record any motion of air and particles through that screen. It's also useful if we want to track sand from which blow tube that fills a certain area by color. And so in this case, I have 6 blow tubes. I've defined a plane on each blow tube, as you'll see later. Run solver setup and check our setup. So what I'm going to do is go back to my grid view here. And then I'm going to load my check setup layout. Sorry, cancel. So here I have, instead of clicking individually here, I've combined all 4 outputs so I can check my boundary conditions. Do I have a blow pressure applied? Yellow. The vents are shown as green. Got my sand. You can see, you can check I got sand fairly far down in plenums and blow tubes. In this case, because we're using it's an initial design, we're using indefinite sand supply, and to cut down to speed up simulation, we're cutting out any dead space, any dead sand that will just eat up calculation time. Typically, we reduce run times by around 20–30% when we take into account and take the time to remove dead sand areas. Got our flux planes, and we got our venting. So when we're happy with the setup, we can go to post-process, start tech plot, which is done already here. So this is the first layout, first set of results. Looking at the sand ratio in the cavity and the particle speed above 0.2 meters of a second. The reason I have filtered out any particles below with a speed less than 0.2 meters per second is that sand moving at that speed or lower is not contributing to any further compaction. So here we see we can stop now. There's really no more sand motion. We might as well just go to the very end of our 1 second. And one thing we notice here is that we got a potential soft area. In addition to those, I've got the steady results at 1 second. So we got core density, and we can see we got soft areas here, potential soft areas here. And matching with last to fill areas, which we can use our fill time map, to quickly give an overview of which areas that fill last, which is typically, from a quick overview, where you could see issues with your design. Another set of results that we can that we'll just do. One is, sorry, that's not the correct one. So in this case, we're looking at sand being colored by which blow tube fills which area, along with the sand mass over time. And if we pause that and go back, we can see as the graph turns horizontal, that indicates that there's no further addition of volume and the cavity is filled. We got a few additional results. So here we look at the tool wear. Given the typical turbulent behavior in the blow tubes, we will see some wear in the tubes, but they are wear parts. So the important part is that we see no or very limited tool wear in the cavity itself. Now, if we did have tool wear, we could examine whether or not it would make sense to potentially have an insert locally under a blow tube for extended tool life. And resin wipe-off prediction by volume of the surfaces that are exposed to resin wipe-off. So with this, and with that area in mind, the next step could be to do a next version with some changed vending. So as Peter mentioned, you easily end up with Swiss cheese, and this is done deliberately as the next step. But we wanted to we wanted to fill this area quicker. So we want to add more vents to allow for increased airflow and have the air drive sand into these areas. So what did we do? Well, we added a significant number of vents around 2 cylindrical holes, as well as added parting line tracks. The reason that there's no end on this side is because we got those vents right here. So how does that turn out? Well, let's look at this. So here, just comparison between the ratio and the particle speed. So the upper two is showing our baseline, and now we can already see here we are 0.15 of a second. We can see a significant difference. Also notice how the path where the sand actually still have to traverse, although the tubes remain open, which is a good thing. We have got fairly extensive paths correlating with these corners still not being full. And here we see a fairly full cavity already. Taking a look at how So in this case, we added a local transient data point right next to the cylindrical hole. And as we play this simulation, we can see how the density builds up over time. We can look at the particle speed conversion, and on this graph, we graphed out the two transient points next to each other. You can see clearly the behavior of the baseline is erratic. We reach a point of timing because the materials are still moving, similar to what Peter talked about in the example of the water jacket with the webbing. They would have seen something like this. We reach the highest point of compaction, and then the particles start to move again until they hit their final resting place, which will be at a lower compaction than when they first stopped before they started to move again. And last but not least, we'll take a look at the flux data and volumes. So although we do not as such increase the volume significantly, because we haven't done any changes, so the volume input as such doesn't change. We maintain the same area, we maintain the same pressure, but by allowing for increased sand, air and sand flow to the center, we increase and improve on the distribution of the particles in the cavity. Plus, we, as an additional benefit, fill the cavity significantly faster, and this leads to a increased process robustness. So over time, your vents will start to run a little dirty, stuff like that. You may not have an ideal seal on your core box. So the faster you can fill a cavity, the more robust the process is. The last thing I would like to show today is an additional feature which is new, that we now have the ability to run a simulation like this and let me just speed it up a little bit. So what we're looking at here is, the tubes run empty. There's really not enough. There might be, but the way it's distributed in the magazine, there's really not sand enough to fill this core. Right? So the solution would be to do a double blow. Okay, so replenish the magazine and blow again. We could not do that in the past, but now we do have the ability to say, okay, well, we can actually fill the magazine again just by gravity dumping sand. Into the blowhead. So graphics is a little, but let me increase the speed again of the animation. So this is just purely sand falling under gravity. So we have no sand in the blow tube. Some sand will actually fill up and flow into a cavity, but Um, so now we have a magazine that is filled with gravity dump particles. And we are ready to continue. And here's our second blow, our second condition, and we can look at what that does when we play that. All right. So now we got a full cavity, and we've done that double blow study. In double blow, it can be cycling through a magazine, looking at sand levels, start out high, just running it down, emptying out the core cavity, refilling it. Can do a lot of useful studies now with this added feature of restarting with a previous sand location. So this is what I had to show. And I will stop sharing my screen and hand you back to Peter and Octavio.
Well, thank you, Thomas. I'm going to take over and share my screen again. And looks like that's coming through. So, Thomas, I'll let you catch your breath while we are getting ready to get to the questions. If you still have questions and have not put them in as we were going, please put them in the Q&A panel. We'll get to that in a second. One thing I just want to do before we get to that is talk about a few next steps. If you do have interest in ArenaFlow or like to speak with us, we will be at the AFS Metal Casting Congress next week. That's Tuesday, Wednesday, Thursday next week in Grand Rapids, Michigan. We're excited to be presenting together with Lempe Reich a paper called Cold Box Core Production Process Optimization using simulation, where will be some introduction to ArenaFlow, but then obviously looking at a case study. That's at 8 a.m. on Wednesday in Grand Gallery A. And also visit us at any time when the exhibits are open at the booth. We'll be at booth 515. You can find us there or reach out to us in advance and be happy to schedule a meeting to discuss your situation, your cores, your tooling, and how we might help. And I would encourage you to try ArenaFlow yourself. It is available for download today. If you have APA-enabled licenses, you can use them today on ArenaFlow, or speak with your account manager if you have questions about how to get started. And then contact us. We do provide support, the same support that we give to our direct sales clients. We provide to APA clients, or contact us if you have any questions about training or how we might help. And with that, we're going to get to questions. So Octavio, I will turn it back over to you.
Thank you for your presentation, Peter and Thomas. So yeah, as Peter said, we'll open the Q&A now. So if anyone has any questions, and if you haven't done so yet, please type them in the chat box, and I will read them as we go. So I'll be starting with the questions. Can ArenaFlow handle sand mixtures?
Thomas, you want to field this one? Or I'll go. Okay, go ahead. Sorry. Go ahead, Thomas.
Yes, ArenaFlow handles sand mixtures very well. As I mentioned, maybe not so clearly during my short demonstration, any particle, whether it's artificial ceramic materials or additives, various sand types, it can, for refractory purposes, you can simulate like a mixture of silicon chromite or silicon zircon, any sand recipe, as long as we have a screen distribution and a solid material density, not bulk density for the input. So yes, we can certainly do that.
Thank you for that, Thomas. The next question is, can you simulate a double blow?
And Thomas, maybe I'll take this one. And I'm suspecting this came in before the last part of the demo, but obviously, as we showed, yes, it can. But there's a couple reasons to do that. So first of all is if you have commonly, if you have a core that is large in comparison to the magazine, you might not be able to fill it with sand in a single blow, even though there's lots of sand left in the magazine. Sand is not a liquid. So it does not just flow down under gravity. It has its own angle of repose, and we're able to capture that. So looking at that, we're able to capture that. And that's really enabled by the new ability to take results from one simulation and use that as a starting point for a second simulation, or a third, as Thomas showed. The other part of that is not just looking at how the core fills under a double blow scenario, but what's happening to that sand shape in the magazine, which can lead to insights into the magazine itself, or strategies when filling, or really how different fill levels affect the blow. If your magazine is depleting between blows, it could be the opposite scenario where you have small cores compared to the magazine. You don't refill the magazine every blow. And so how does core filling quality, how's that affected by sand magazine level? You can do all those sorts of things now with that new feature.
Thank you. The next question is, can I customize layouts?
Yeah. What was really cool, what Thomas showed there is we didn't do a lot of demonstration, but there's a lot of predefined layouts. So when you go to post-processing, which is where you spend most of our time, on the right, there's this whole tree of options of common things you would look at. And you can click at it, and it'll instantly bring up views that most people would care about. But what Thomas did there is made some common layouts. And once you have those, you can use those to quickly look at results, can compare different cases, to display multiple things at once. You can take those views and rotate around. And all of those were customized layouts that Thomas made. And yes, you can make your own that really speed up your workflow during and make your post-processing more powerful to communicate those results, right? Because you learn something, but then you want to communicate that, with management, maybe with your customers, maybe with people on the foundry floor, and it gets everybody on the same page quickly with those customized layouts.
The next question is, do I need to type in all vents in the GUI?
I think I heard, do I need to type all vents in the GUI? Thomas, do you want to talk about how you get vents into the GUI or into the arena flow?
Let me try to explain. So let's say you have your tooling model in a CAD software, and then most softwares would be able to output like a whole schedule, so that you could send that to a toolpath, or pattern shop. And this is really the information we need as the input for arena flow. So we can easily convert that. Some vendors even have customized macros that will do that translation automatically. And it's really beneficial to use your inputs from your CAD software. Now, obviously, you can, if you need quick changes, smaller changes that you do not necessarily want to fire up your CAD for, or you do not readily have access to your CAD, then can do manual additions or subtractions in the vent table. But I would strongly encourage that you do predefine or use your predefined locations. So no, you do not have to type. It can be fairly automized and extract the information directly, and it saves a lot of time too. Plus ensures that you get the right locations transferred between what you simulated and your tool. And that's, something that we can, in a startup process, we can help with and customize that process of creating predefined vent tables.
Thank you. And the last one that I have here is, how do I set sand flowability for my process?
Well, maybe I'll start, and then Thomas, you can add more commentary if necessary. One of the big differences for different processes, shell sand, when it's not heated, flows quite well. Cold box is obviously sticky. Organics tends to be stickier. This is not a scientific term. Somewhat is. But then you have other variability, right? You have your binder in cold box, it could be aged. Your vents could get clogged. And so which case are you simulating? The first clean blow, the 20th blow, right before you clean your vents. And so first of all, if you have a 5% scrap, we probably don't want to simulate the 19 out of 20 that are good cases. You probably want to solve that 5% that are not. And so that's what one of the things the flowability model is used for. So if you have different processes, there are different defaults for how the sand flows, but you have additional controls in the GUI, and even, like I've mentioned, arena flow is extensible, so you can modify that further. So typically what we'll do is we'll run a base case and compare against existing data if you have it. If you're making new tooling, you're going to be conservative and assume your sand is less flowable than typical. And we can help with that. We usually correlate with, if you're solving a problem on a core that you do have scrap. But if you do, please contact us. We're happy to talk through what can be done. But there's a lot of cases where we'll run different flowability settings and see which correlates with what you're seeing, and then use that moving forward to predict changes. But Thomas, if you have anything to add on that, please do.
No, I think you covered it pretty well.
All right.
Thank you.
Thank you. And seeing as how we have no further questions, that will conclude today's presentation. Just a reminder that we did record today's session. I will let you know where it's going to be available. And thank you again to our presenter from CPFD, and thank you everyone for joining us today.
Yeah, thank you everybody.
Thank you.
Thank
Goodbye.
you.